Hello, PreCalc. You'll be observing this after Monday's class, so that'll be the 30th of January. And we have a definition. It's a new definition, a locus definition. So we'll fill in the blank in a minute. So let me zoom out a little and get the whole definition. It's growing. A blank is the locus. That can mean location or the set. Of all points x, y in a plane, the difference of whose distances from two distinct points called foci is a positive constant. So if you look back at the ellipse work, you'll see that the word was the sum. So we're finding another conic section, and this conic section follows this rule. So let's see if we can develop a picture to help us name it. So let's see, it says there are two fixed points, so I'll pick a point. This is one focus. Another point, that's the other focus. So there's the two distinct points. Means they can't be this distinct, meaning they have to be two different points. All right, so let's pick a point and say we'll call this point on the conic section. So the distance from the first focus to this point is d1. And the distance from the second focus is d2. So we're talking about a difference of those this time. So we have d1 minus d2 is some constant. That will never change in this problem. So I have to find another point where d1 minus d2 equals k. So I'm going to make this one a little longer, d1. So that's my new d1. And this is my new d2. So that's d2. So d1 got longer, d2 got longer, but their difference is the same. So, and there's a point out like that. That is true. And they keep going like this. All right, so there's some other ones I can find as well. And say I start, I don't know, maybe right here. Right there. So let's say that this is distance 1, quite a bit shorter than this one was. And here's distance 2, quite a bit longer. Here, d1 minus d2 would be negative because d1 is much shorter than d2. But it doesn't say anything about the order, it just says their difference. So over here on this side, I'm going to think of d2 minus d1, their difference. And that could be the same as these were on this side. So I'm going to find another point. d1 got longer, but so did d2. And their difference, d2 minus d1, could be the same. And so on. And there's some points. There's a point right in between where this is true. d1 minus d2. d2 minus d1, I mean. And then over here, d2 minus d1. d1 minus d2, whichever way comes out positive. All right. So this one looks a little too far. So maybe here. Let me fix these a little. All right. So once I draw the whole thing, there's a section that looks like this, and there's a section that looks like that. So this has, each of these figures has two parts. We haven't seen one like that. And when we had our parabola, so this is in your thought cloud. Let's see, when I have your parabola, So I'll grab Ryan's thought cloud. When he saw that, he said, looks something like a parabola, except there's two of them. So in the parabola, Ryan remembers, and he's reminding all of us that this parabola gets larger, fatter and fatter, we'll say. So I can, as it goes out, even though it's growing fatter slowly, it will eventually cover the whole number line. So even though when we go way up, it gets fatter and fatter. These are not getting fatter and fatter. They are at a certain bend such that I can find let me give myself a line. I can find a line like right here and a line right here that actually these edges or these sides of the figure will never touch. These are like fences, and they will never touch the fence. And we call these fences asymptotes. Over here in the parabola, any line I would draw like this and like this will eventually be crossed, because these will get, as we go out further and further, they get wider and wider, and they will cross these fence posts. Not so with our friend over here, which I'll now name, and that is the hyperbola. Alright, so the hyperbola has two sections. They are bounded by asymptotes, and these asymptotes will help us actually graph these. Alright, so this particular one, where the openings are left and right, are called horizontal hyperbola. And I will give you the standard form for that one. So here's the horizontal hyperbola in standard form. Wait a minute. My camera's falling off the world here. Alright, there we go. So horizontal hyperbola in standard form looks like this. Notice very similar to the ellipse, except the sign right here. It's identical. And HK, Hector and Kyle, come out. Opposite sign connected to the X, opposite sign connected to the Y. So HK this time represents the center. I don't think I've ever sneezed on video. Alright, center. HK. Let's look up here, and you'll see the center is not on the hyperbola at all. It is the intersection of the asymptotes. Right, the center is there, and that will help us also in graphing the hyperbola. Alright, so let's think of what it might look like if it is vertical. So I won't develop the process like we did up here for the horizontal. I'll just give you an example of what I mean by vertical. So if we have a vertical hyperbola, it would have some fence posts like this. Those are the asymptotes, and it would look like this. The openings are up and down. There's the center. So, all right, so that's an example of a vertical hyperbola. All right, so the name for that one is going to be y minus k quantity squared over a squared minus x minus h quantity squared over b squared equals 1. And again, similar to the ellipse, except right there. All right, so you have to look right there to see if you're dealing with an ellipse or a hyperbola. So a negative sign says hyperbola. All right. Show you where that is found on the conic, where this is our last conic section we're going to study. So we have done circle, parabola, ellipse, and now hyperbola. This is our cone on a cone. And if we're looking at this, where do we find the hyperbola? This is the hardest one for me to draw, but we're going to take our sharp plane and we're going to cut through our cone like this. And the intersection, if we look inside, in the intersection where this plane cuts this cone, would make these kind of intersections. So that's our hyperbola. All right. So again, we always have a cone on an inverted cone, and we cut it through at different angles with a sharp edged plane to form the conic sections, of which the hyperbola is the last for our study. All right. I'm assuming in class, since we have shortened classes this week, that you are still working on your ellipse work. So with that still going, I think I'll just introduce the hyperbola tonight and show you how to graph one from an equation tomorrow. That'll be plenty of time, I believe, for you to, I think I can spread this out. There'll be plenty of time, and that'll allow you to catch up to my videos. All right, so if you do need to go on to your hyperbola work, I'll show you how to do one in class. All right, have a good night and see you in the morning.